What up, everybody? This is Mr. Stan. Today we're going to be looking at a projectile motion problem, and this is one where there is no vertical velocity at first, right? A rock in this case is rolled off a cliff, and it's going 4 meters per second, but that 4 meters per second is going to be horizontal velocity, not vertical velocity, right? And then it hits the water 5 seconds later, and we're going to fill out these graphs down here below it and talk about how high the cliff is, how far away it lands, and we can find all that information. Right? First of all, two things we know about a projectile motion is that the acceleration in the horizontal direction is 0, right? So I'm just going to put a 0 here on the bottom left. Right? And that tells us that it's not going to speed up or slow down in the left or right, because gravity accelerates things downwards towards the Earth, not left or right. Right? However, in the vertical direction, right, we're going to put a acceleration of -10. Right? So as we've talked about before, gravity accelerates things at roughly about 9.8 meters per second towards the Earth, right? And that's true anywhere near Earth's surface. In this class, we round it to -10 to make the math easier. Okay, the other thing we know here is that the rock was in the air 5 seconds before it hit the water. So everywhere where there's a time axis, and that's pretty much all of these, we're going to put a 5. So 5 goes there, 5 goes there, 5 goes there, 5 goes there, right? And 5 goes there. But then when we get to this one, you still have a 5. Okay, so at 5 seconds, it was in the air. And now we're just going to make the shapes of the other graphs, right? Horizontally, the velocity shouldn't change, right? So it should be a flat line for the graph. And we're told in the problem that it's moving at 4 meters per second, right? Vertically, what is the velocity going to be, right? We know that because it's rolling off of a flat surface, at least that's what we assume, that it's going to have a vertical velocity of 0 in the beginning, right? As soon as it rolls off the cliff, gravity is going to speed it up, but it's going to speed it up starting at 0 and then get faster and faster, right? And then that velocity would go down from there, okay, as gravity pulls it down. Right? Keep in mind that the vertical velocity graph here should have a slope of -10, because that's what the acceleration is. Right? Now let's go over to the horizontal position graph. All right? If you have a constant velocity, this would be a straight line. Right? And the slope of this line should be 4. Okay? And we'll assume that's the case. Right, and then for the vertical position graph, it's going to start up. If the water's 0, then it's going to start up here. It's going to be slow at first, so you have a line that's not very steep, and then it's going to get steeper and steeper and steeper, and should hit the water at 5 seconds. Right. So you should have a line that curls down and then hits 0 at 5 seconds. Right? And that's not a perfectly. It should be smoother than that in real life, but that's what we have to work with. Okay, so a couple principles about these graphs. One is, if you find the area under a velocity graph, that tells you the displacement that you can use on the position graph, right? And if we're going the other way around, let's pretend like it told us what the displacement was, and we didn't have this velocity here, then we would use the slope of this line. Okay, so we know that the slope of this line is equal to 4, right? Sorry. Right, the slope of that line is equal to 4. Now, if we take the velocity graph and we just shade it in, right, and find the area of this shape, and this shape is a rectangle right there. Okay, we find the area of that shape, then the area of that shape is going to tell us how far it went. Right? It's going to tell us how far it went horizontally, because we're in the horizontal direction. So the area of a rectangle is base times height. All right, and in this case that would be 4 times 5, so 4 times 5. Sorry about the weird 5 there, is equal to 20. All right, and so the 20 would actually go right here. Okay, because that is the horizontal position, so that tells us where it was in any time. So the horizontal position should be 0 in the beginning when the rock rolls off the cliff, and then it should be 20 at the end because the rock is going to go over here and splash in the water somewhere. So it'll be 20 meters from where it splashes in the water to the bottom of the cliff. Okay, so vertically we can do the same thing. All right, so we take the area between the area of the velocity graph, right? And it'd be the area between the line that's telling us the velocity and the 0 line. It's right here. Okay, this time it's going to be a triangle. So the area of a triangle is 1/2 of base times height. So we'll have to figure out what that is. All right, and we don't know the height. So how are we going to do that? Recall that the acceleration vertically is -10, which means every second that goes by, the velocity is going to increase by -10. So it's going to be 0 in the beginning, then -10, -20, -30, -40, -50. All right, so 5 seconds go by. It's going to be this number, the time, multiplied by 10 will give you a velocity of -50. Okay. All right, and so base times height would be 1/2 of, below it, -50 for the height, and then 5 for the base. Okay, and so if you put that in a calculator or figure it out in your head, it would be -125. Okay, so what does it mean, -125? Okay, all it means is that you notice it started up here somewhere, and the ball vertically went down to 0 because we're counting the water as 0. And so to move -125 and end at 0, it would have had to start at 125. So we're going to put 125 right here. Okay, and so we've figured out everything. We figured out that the cliff had to be 125 meters tall, because that's what we got as the vertical position here. And we found that the rock had to land 20 meters away from the bottom of the cliff. Okay, different problems give you different information, so let's pretend like it didn't tell us it was 5 seconds later, but it did tell us the vertical velocity. If we had that it was 50, it hit the ground, the ground or the water at 50 meters per second, you just divide that by 10 to get this number, right? And this number is a time. You could put that everywhere else. So you could also work backwards here. Just keep in mind on the horizontal, slope of this line is equal to the value here, all right? So the slope of this line is 4, the value is 4. And then the overall displacement, the number that goes on top here, is equal to the area under this graph. Right, so depending on what they give you, you would either find the slope first and then put that number here, or you'd find the area and put a number here, right? Okay, now let's talk about a little bit, before I end the video, about what would happen if this cliff was shorter, right? If this cliff was shorter, then this graph would start down here, but it would not be in the air as long, right? So the time would not be 5 seconds. It would be less. And you can imagine if the time was less than 5 seconds, let's say it was 2, then over here on the horizontal graph, they all have the same time, so this time would be 2 seconds as well. All right, and you could get 4 times 2 instead of 4 times 5. And so basically what you would get is you get a horizontal displacement that was smaller. Right? So the smaller we make the cliff, the less time it spends in the air, and the smaller the horizontal displacement is going to be. So it's not going to go as far from the cliff if the cliff is shorter. All right. Another thing we could do to change how far the rock goes is to change the velocity. All right. So let's say if you were to double this velocity, then this number here would double, and you get a bigger area, all right, which means the rock would go farther. All right. So a faster object would cause it to go farther, and also a slower object would cause it to go less far. A shorter cliff would cause it to go not as far, all right, even if we don't play with the velocity, just because it's not in the air as long. Likewise, a higher cliff would cause it to go farther because it's going to be in the air longer.